In this video we are going to see why neural networks can be seen as solutions of differential equations and why this can be useful. We will get back to this animation later on when this makes a bit more sense than now. So deep neural networks are a very important concept that has been developed in the last decade or so, and mathematically they are not something very complicated, at least to describe and introduce, because they are essentially a highly parameterized function whose parameters are the degrees of freedom we can play with in order to approximate a target function and solve a task we are interested in solving. And in particular, the building blocks of these networks that allow us to call it deep neural network are potentially a lot, and they are called layers. The layers are themselves parameterized functions, and usually they are quite elementary. The parameters of the network, that are also usually called weights, are found through an optimization procedure, so in a data-driven manner, where what we do is minimize or optimize a certain cost or loss function that is designed so that it is zero in the ideal case in which we exactly solve the task at hand. The reason why these models, and in particular deep neural networks, are very popular nowadays is because they tend to be very flexible and highly expressive, so they allow us to reproduce a lot of interesting functions, or at least approximate them to a desired accuracy. There are a lot of different deep and shallow neural networks, and those I'm going to focus on today, and also those that allow us to introduce a connection with dynamical systems, are the so-called residual neural networks. So a standard feed-forward layer of a neural network, like the multi-layer perceptron we started from in the 50s, is fairly simple as a map, because it's a map where everything is parameterized. So we take an input x, and we pass it through a function f of x, which defines our layer, and that's the usual kind of pipeline of an arbitrary layer of a network. A residual layer, which is the fundamental building block of residual networks, is slightly different, because we don't parameterize the map entirely, but we parameterize only the residual that this map has compared with the identity, so how far this map will be from the identity. This means that instead of just having x which is mapped into f of x, we will map x into f of x plus the input itself, plus x. So we will take x old, or the current version of our input, our image for example, and we return itself plus this function f, which might depend on some parameters, evaluating not just at the parameters but also at the current position x old. There are several reasons why this is a clever idea and why this was introduced. Intuitively, this is because, especially for deep architectures, we don't want our layers to do a lot of effort, to do a lot of work, because we will essentially distribute the work throughout the depth of the network. So the idea is that each layer should be fairly close to the identity map, and f is then allowed to be rather small in terms of weights, and also the signal propagates much more nicely. Since my goal today will be to show a connection between neural networks and dynamical systems, let's introduce a little bit what I mean with dynamical systems. And in particular, dynamical systems are described by systems of differential equations. They could be ordinary or partial differential equations, but those I'm interested in, especially in this video, are time-dependent differential equations. And they are very popular in applied mathematics and in mathematics in general as a modeling tool, because they allow us to describe anything, or potentially anything, that is evolving through time. So any quantity that changes through time can be described in terms of instantaneous rate of change. So in terms of how a quantity of interest changes through time, and hence how the derivative with respect to time of that quantity is defined, is modeled. So in particular, what we can do is define a so-called vector field f, which has the same dimensionality as the state we are observing, and we decide that f is a good candidate for describing the rate of change of this quantity of interest. X could be a position, it could be the momentum, so the velocity, for example, of a particle, or it could be a lot of other quantities that we are tracking of our underlying system. Now, in general, it's impossible or extremely hard to exactly solve differential equations, whatever the differential equation we are interested in is. So this means that if we want to take something out of this nice modeling assumption, we need to introduce some numerical approximation. We need to make some simulations of our target differential equation. And this is where numerical analysis come into play. And in general, there are a lot of different methods. There are graduate courses entirely focused on numerical methods for ODEs and PDEs, or structure preserving methods for these kind of problems. But for us today, it will be more than enough to take a look at the simplest method possible, which is the explicit Euler method. So the idea is that we do a very rough local approximation of the vector field and of the solution, because we assume it's just behaving linearly. So what we say is that the solution at time tn plus 1, or tn plus h, is nothing else than the current position xn plus a step of size h, which is the time delay we have from time tn to time tn plus 1, which is multiplied with the vector field f evaluated at the current state, so tn xn. And why do we care about the explicit Euler method in a video on neural networks? So the idea is that there is a very nice and intuitive connection between the residual layer of ResNets and the Euler step of dynamical systems. Okay. So the idea is that the residual layer does something which is quite simple. It updates the current position with an additive perturbation, which is parameterized by f. Okay, depending on a set of parameters theta n, potentially varying with n or also fixed. The Euler step does exactly the same. The difference is that in principle f is not a parameterized function, it's not a parametric vector field, but it's just a fixed one that could be time dependent. So the idea is that these two maps are actually very close, and we can make them coincide if we think a bit about what it means to model, to design a layer of a network. In fact, a neural network, as I said at the beginning, is nothing else than a parametric function. So we have a lot of freedom in how we model this layer, a lot of freedom in how we design this layer of a network, and in particular how we choose f to be. So this means that there's nothing wrong with saying that actually these maps are the same map, and residual layers of residual networks are nothing else than the Euler step of a suitably parameterized ODE. This is like a simple way to see why we can think of neural networks, and in particular some types of neural networks like ResNets, as discrete solutions, discrete approximations to dynamical systems and hence differential equations. There are other connections, for example neural ODEs, that I might explore in other videos in the future, and let me know in the comments if you're interested in this. Before getting back to the animation I started from in the first slide, I want to make a remark which I think is very important, which is that here we are just making an assumption, which is that we model each and every layer of our network based on some ideal dynamical system, ideal physics that we are introducing behind it. But in principle, there's no real dynamics, right? Our neural network has no physics behind it. This is nothing else than a modeling assumption that we are introducing because hopefully it simplifies some of the design or the understanding of the network we have in front of us. I think it's very important to see a geometric representation of this connection, in the sense that now that we have this clear understanding that residual layers are nothing else than discrete approximations to solutions of differential equations, we can also think to what a neural network is doing to our inputs. Because essentially our network layers are doing nothing else than an iterative transformation, an iterative update of the initial configuration of our points into a final configuration where the task we are interested in solving is easier to solve. For example, in this case, I've trained a ResNet based on the hyperbolic tangent to classify two classes of points, the yellow and the cyan points. And the idea is that usually what we try to do when solving this simple task is arriving at a transformed version of the input points at the final layer, where the two classes of points are linearly separable. So you can put a plane in the space and say on top of this, on the right of this, the points are all yellow, and on the left or the bottom they are all cyan. So as you see here, I didn't prescribe anything on the dynamics, but if we plot the evolution of the points after each and every layer of our network, what we get is exactly a natural way that is learned in a data-driven manner to linearly separate the two classes of points at time 1, which is exactly what we want. So this is quite a good intuition we can have of what a neural network is doing. It's nothing else than acting as the solution of a differential equation, or at least some types of networks like those we are exploring in this video. This is all nice and good. It's interesting, especially if you like dynamical systems, but is it really an important connection that we are making, or there's no point in what we are doing other than just fun mathematics? My point is that this connection is very important, especially for the mathematics of deep learning, because it allows us to borrow from other areas of mathematics, which are much better developed than the mathematics of deep learning, and we can take ideas from those areas through this connection with dynamical systems to design new neural networks that behave in a better way, in some sense, than the existing one, or also potentially understand why the existing one work as they work, or when they fail, for example. So the idea is that now that we have a differential equation behind the network layers, we can say what happens if we change this differential equation and we get unconventional residual layers. Can we do something better? For example, can we construct neural networks that are constrained in some particular way? Or can we better propagate the signal, for example, preventing vanishing and exploding gradients to show up? So these are all ideas that we can look into, especially taking ideas and methodologies from, for example, dynamical systems, numerical analysis, and structure preserving numerical methods, for example. And these are some books that I think are very good in these areas. There are many others. But is more or less like the main advantage of introducing this connection between differential equations and neural networks. There are a lot more. For example, one can use these ideas, this connection, for approximation theory, but we can introduce and discuss these topics better in the future in other videos. I want to conclude with one of the examples of the success of this change of perspective, essentially, that we are exploring in this video, of looking at a neural network as a discrete approximation of a differential equation. And a very good success story from my experience, my point of view, are symplectic neural networks. So there's a lot of research which has been going on in the last 5 years or so on designing neural networks which are symplectic, or neural networks that are designed to approximate the solutions to Hamiltonian systems. So if you're not so familiar with physics and classical mechanics, you probably have encountered in a basic course in classical mechanics, or at least high school level, systems that have some kind of conservation of the mechanical energy, so potential energy plus kinetic energy. Most of these systems can be phrased in a very elegant formalism, which is the one of Hamiltonian systems, where essentially this sum of kinetic and potential energy is the only object we need to fully describe the dynamics. But then there's also a very strong geometrical framework that allows us to characterize this system, which is the one of symplectic geometry. And in particular, you can think to the symplectic form as kind of a volume form. So as you can see here, it's very important when trying to simulate systems which behave in a conservative manner, so in particular that are Hamiltonian, that when we simulate them, especially for a long time, for example, for planetary simulations, for n-body problems, or molecular dynamic simulations, we need to use methods that try to preserve this symplectic structure that is preserved by the exact solution, and possibly also to conserve the energy, the mechanical energy or the Hamiltonian energy of the system. And you can see here a simple example, and I will go deeper into in other videos on this, where if you use a method which is symplectic, so it's compatible with the desired structure of the system, then you can simulate for a very long time, and the energy is almost conserved, and the simulation of the three particles is very stable. On the other hand, if you use the explicit Euler method that we saw before, which has the same accuracy in principle for short-time simulations, at the beginning the simulation seems kind of okay, kind of reasonable, but then it's extremely unstable and the energy blows up. We just have a simple example of why enforces some kind of structure in the numerical approximation of the solution is important. This is the same also in neural networks in some situations, for example, when simulating Hamiltonian systems, learning the equations of Hamiltonian systems from data. And there's a bunch of research that is going in the direction of using the ideas from numerical analysis and dynamical systems for Hamiltonian systems to design and discover them from data or just simulate them from equations. So you can just take a look at some of these papers. This is also one I worked on. And the idea is that one can build on this connection to design networks that behave as desired, for example, because they are symplectic. Okay, so you can find some examples here of what this connection can buy us, and there are many more that I will try to explore in future videos. So this is everything for today's video. Let me know if you have suggestions for future ones. Otherwise, see you in the next video.